Very well, so in this video we're going to start with chapter 1 of our textbook, Number and Algebra Basics. So let's talk briefly about the learning objectives of this chapter. By the end of this chapter, you should be familiar with the following: using approximations, bounds, and percentage error. Um, that is to report numerical information to different levels of accuracy and evaluating the validity of calculations. You're going to learn how to simplify exponential expressions using the laws of exponents. You're going to learn how to write numbers in scientific notation and how to complete computations relevant in the real world. You're going to learn about logarithms as the inverse of exponents, and you're going to evaluate simple logarithmic expressions, and you're going to solve exponential equations in the form a to the power of x equals b. So those are the learning objectives for this chapter. The first topic, which is topic 1.1 of the chapter, approximations and error. So this is really about rounding, okay? So let's review a little bit about rounding before anything else. Let's suppose we have a number such as 4.375. You have a number like that. And you're going to be asked, let's say, round this to the nearest whole number. So 4 is the whole part. And what you have to do is check the first decimal place. In this case, it's a 3. Because it's less than 5, then you would just round it to 4. So that would be 4.375 rounded to the nearest whole number. Sometimes you're going to see a notation which will be like d dot p, dp. And that just means decimal places. Decimal places. So for example, they might ask you to round the number 4.375 to 1 dp. That just means to one decimal place. So in that case, we would have to check the second digit after the decimal point, in this case 7. Because 7 is larger than 5, then we would have to round it to 4.4. So this would be 4.375 rounded to one decimal place. Okay, so what we have here to the right are the rules for significant figures. Now, this significant figures really have to do with zeros in a number, right? So for example, if you have a number like 2300, 2300, the only significant numbers here are 2 and 3. Okay? One way to think about it is, how can I write this in scientific notation? You could write it as 2.3 times 10 to the 3. So notice that you only need these two digits, or these two numbers or digits to be significant, right? So only 2 and 3 are significant. So that means that zeros to the right are not significant. But zeros become significant when they are bound by non-zero digits. For instance, they mention here the number 230, wait a minute, 23,001, sorry, 23,001. So if we have the number 23,001, although it has zeros, but because these zeros are contained between non-zero digits, they're considered significant. So that means that the number 23,001 has 5 significant figures. And notice you can think again of this in scientific notation, because you would have to write 2.3001 times 10 to the power 4 to represent that number in scientific notation, meaning that all the digits are significant, all 5 digits. Very well. So it says now that zeros to the right of a whole number or to the left of a number in decimal expansions less than 1 are not significant. So for instance, the number 4,500 has only two significant figures. And the number 0.005 has only one significant figure, meaning that these zeros are not significant. Now think of scientific notation again. 4,500 we could write as 4.5 times 10 to the power of 3. And 0.005 we could write as 5 times 10 to the power of negative 3. So notice that only one of the digits is significant for 0.005, and two are significant for the number 4,500. Finally, point 4, it says that zeros to the right of a number in a decimal point are significant, as we can assume that they represent additional levels of accuracy. For example, 2.30 has three significant figures, as the zero in the hundredth position is significant. So that means that if you have 2.30, this zero is significant after the decimal place because it's telling you that this is a measurement that has an accuracy to the hundredth position. So if we had another zero here to the right of this zero, this would also be significant because then it would mean that your accuracy would be to the 1,000th position. Very well, so here we are with example 1.1, and it says part A, round the number 10.562 to 1, the nearest whole number. Okay, so that means that they only want us to write the whole part of this number, but notice that we have to round it up because of the fact that we have a 5 in the 10th position, right? So we would have to round this to 11. So that would be the nearest whole number to 10.562. Rounded to two decimal places. So that means that we would write 10.56 because the number after 6 or the digit after 6 is a 2. Therefore, we don't round up. To three significant figures. So we would write this as 10 point, and here we have to decide what to use as the first decimal. And that would be a 6, right? Because the number after the 5 is 6, which is bigger than 5. Therefore, we have to round up. So we end up with 10.6, and this is rounded to three significant figures, right? Remember that the zero that is bound by two non-zero digits is significant, so 10.6. In part B, they ask us to complete the table. And they give us a quantity on the left column. And the middle column, they ask us for the number of significant figures. So let's do this part first. So if we have a number like 25,400, this obviously has three significant figures. Those are the three significant figures it has, the 2, 5, and 4. 0.006 has one significant figure. 0.3052. Okay, so that first zero is not significant, right? The placeholder. But this other zero is significant because it is bound by non-zero numbers. Therefore, this has four significant figures, which would be 3052. And then finally, we have this number, which is 40.00560. Now, notice that all these zeros after the decimal point would be significant. First, because we have three zeros here that are bound by the 4 and the 5, but also this last digit is significant because of the accuracy. We mentioned that property as number 4 in the last slide. So that means that this quantity has 1, 2, 3, 4, 5, 6, 7 significant figures. Okay, then here to the right in the last column, they ask us to do some rounding. So they want us to round 25,400 to two significant figures. So that means that I have to write 2 and 5 and then decide, well, I had to decide whether I would round up or down or just leave it the way it is, sorry, right? We don't round up because the next number is a 4. So 25,000 would be rounding to two significant figures. 0.006 is already rounded to one significant figure, so we would just leave it the same, right? 0.006. 0.06. Um, Next, they want us to round 0.3052 to three significant figures. So that would be 0.305. And we leave it like that. We don't round it up because the next digit is a 2. And finally, we have to round 40.00560 to four significant figures. So that would be 40, that's 2, 3, and then we have the fourth. So we have to decide whether we leave it as a 0 or round up. Notice that the next digit is a 5, so we would have to round up. So 1. So 40.01 would be rounded to four significant figures. Very well, so next we have example 1.2. And it says, use estimation to calculate each of the following, then do the full calculation and write your answers correct to two decimal places and three significant figures. So let's start with letter A. So in letter A, for estimation, that just means rounding very quickly and then adding up the numbers. So notice that we can round 2.67. We can just round that to 3 plus 3.94, which is almost 4. And then we can estimate that the sum should be somewhere around 7. But if we do the exact sum, where we add 2.67 and 3.94, we're going to get 6.61. And notice that this is already to two decimal places, and also it has three significant figures, so we don't really have to do anything else. Three significant figures. Okay, so for B, I'm going to write it here. It says, again, use an estimation. So 5.23, we could round it to 5, and 4.89, we can round that to 5 as well. So we have 5 times 5 equals 25. So that's an estimation. Now, if we do the exact calculation, if we put in the calculator, we go 5.23 times 4.89, we're going to get approximately, or we're going to get exactly actually, 25.575747. So let's round first of all to two decimal places. So that involves up to the 7, but the next number is a 4, therefore we don't have to round up. So this would be 25.57. But if they ask us to round it to three significant figures, then we would have these three digits as the three significant figures, but because we have a 7 after the 5, we would have to round the 5 up to 6. So this would end up being 25.6. Okay, so now for letter C. For letter C, let's do a quick approximation. We can say this is the same as 3 times 8, right? Let's round the 3.25 to 3, the 7.52 to 8, and this divided by 4. If we do the math, this is going to give us 6. So that is a pretty good estimation. It should give us around 6. But if we do the exact calculation in the calculator, we put the 3.25, multiply that by 7.52, and the result of that divided by 4.37, we're going to get that this equals 5.5926773, etc., right? That keeps on going. So if we want to round this to two decimal places, that means we have to take into account this. The third digit is lower than 5, so it stays the same. So 5.59 would be rounding to two decimal places, but also to three significant figures, so we don't have to change it. So the next example in the book is 1.3, and it says a rectangular wall of length 8.11 meters and height 3.82 meters is to be painted. A can of paint costs $5.69 and can cover an area of 5 meters squared. A. calculate the area of the wall first by estimation and then using a calculator. Write all the decimal places shown by your calculator, then write the area correct to 2 decimal places. Okay, so let's start with letter A, and we can do it by estimation by saying that it's about 8 meters times 4 meters, therefore approximately 32 meters squared. But they want us to calculate now the exact area using a calculator. So if we plug in 8.11 and multiply that by 3.82, we are going to get 30.9802. And it says write all the decimal places shown by your calculator, then write the area correct to 2 decimal places. So notice that that would just be approximately 30.98 meters squared. So notice that our estimation was off by more than 1 meter squared. Part B, calculate the number of cans that are required to paint the wall. So for part B, what we need to do is divide the area, a total area, by the area covered by each can, right? So that would be 30.98 divided by 5, and that's going to give us 6.196, right? Or, approximately 6.2 if we want to round. That means that we need a little more than 6 cans, so we would have to buy 7 cans of paint. 7 cans of paint, and we would have quite a bit of paint remaining, so you can paint something else. And then for part C, it says find the cost of painting the wall reported to a suitable level of accuracy. Okay, so for C, the cost of painting the wall, since we need 7 cans and each can is worth $5.69, $5.69, this would give us approximately $39, $39 with 83 cents. 83 cents. Now, one thing you can't not forget in the IB exams, especially, or tests, is using units, right? So if the question is about money, you have to put the dollar sign or whatever the currency is. You have to write cans, you have to write meters squared, you have to write meters, and in general, just any unit. Okay, so now we go to example 1.4. And it says for the rectangle in figure 1.1, so this rectangle over here, find the exact length. So that word is important, exact. The exact length of the diagonal D using roots. Then the complete decimal expansion from your calculator and correct to 3 significant figures. Okay, so for A, first we need to find the exact length. For that, we can use the Pythagorean theorem, right? If you notice, the diagonal of the rectangle is also the hypotenuse of a right triangle because this angle here is, of course, a right angle. Therefore, we can say that D is equal to the square root of 7 squared plus 4 squared, and this would be equal to the square root of 49 plus 16, and this is equal to the square root of 65. So this is an exact length. So this is exact. That's what they mean with the word exact, meaning that if you have an irrational answer, like square root of 65, in order to express it exactly, you have to express it with the square root. Next, it says the complete decimal expansion from your calculator. So if we do square root of 65 in the calculator, square root of 65, that is going to give us 8.062257448. And then if we want to round this to 3 significant figures, that would just be 8.06. This would be to 3 significant figures. Next, we have part B. Part B, and this is more like a typical IB examination question. So it says a circle has an area of 10 centimeters squared. Find the exact length of the radius r using roots and pi, then showing the complete decimal expansion from your calculator and correct to 3 significant figures. So let's recall that the area of a circle is found by calculating area is equal to r squared pi, right? R squared times pi. What this implies is that we can rearrange this equation. We can say, well, r squared should equal pi over the area. Or, in other words, the radius should equal the square root. Oh, I did this backwards. No, this would not be pi over area, but rather area over pi. So let me correct that very quickly here. So area over pi. So therefore, the radius would equal the square root of the area over pi. And in this case, they're telling us that the circle has an area of 10 centimeters squared. So what would be the exact length of the radius? Well, the radius, the exact length would be equal to square root of 10 over pi centimeters. Don't forget the units. So that would be the exact radius. Then it says, well, how about the complete decimal expansion? So we would have to expand the square root of 10 divided by pi. And that's going to give us quite a long expansion, like 1.784124116. And then it says round to 3 significant figures. So up to here, we don't have to round up because the next digit is a 4. So it would be equal to approximately 1.78 centimeters. Let's not forget the units. Very well, so the next topic we have to cover is something called bounds. And the definition would be like this. If a measuring device gives a reading of x and has a level of precision p, then the bound is in the form of x minimum is less than or equal to x, which is less than x maximum, where x minimum is equal to x minus p halves and x maximum is equal to x plus p halves. So I think this is easier to explain with an example. Let's suppose we get a reading. So this is a ruler, and the ruler has a precision of 1 millimeter. So P would be 0.1 centimeters. Therefore, P halves would equal 0.05 centimeters. Then if we get a reading of 2.3, that would be our x, right? X would equal 2.3 centimeters. And what this means is that our x minimum would be 2.3 minus 0.05. So that would give us 2.25 centimeters are less than or equal to x, which should be less than 2.3 plus the 0.05. That would give us 2.35. And let's not forget the units, centimeters. So notice that this tells us that if we measure 2.3, we are actually not exactly at 2.3, but rather it's a value between 2.25 equal to or greater than 2.25, but less than 2.35. Now we say less than 2.35 because if it were exactly 2.35, we would have to round it up to 2.4. So next we have example 1.5, and it says find the bound for each of the following measurements given the level of precision and draw the bound on a number line. Okay, so in this example, I'm only going to do letter A, and you guys can do the others as practice because it's the same procedure. So let's look at example A. It says mass M, so M is equal to 42.3 kilograms. And it says that the precision of the instrument they're using to measure the mass is 0.1 kilograms. That means that p halves would be 0.05 kilograms. Okay, so then if you want to find the bound, remember that we put m, which is the measurement we made, in this case the mass, is greater than or equal to m minus p halves, right? So this would make it 42.25, right? 42.25 kilograms, 42.25 kilograms, and m would then be less than 42.35 kilograms. So how do we represent this on a number line? So if we have a number line, which is just an infinite line, and we're going to say that this is m over here, somewhere here, right? Not exactly there. The measurement we took was 42.3, but remember that m is bound here. So we could write here, let's say 42.35 kilograms on this part, and on this other part we could write 42.25 kilograms, and m would be equal to this, but less than that. That's what the open circle means, less than, but not equal to, whereas here it can be greater than or equal to. So this area here would represent the bound for m. All right, so next we will work with example 1.6, and it says a rectangular picture is to be framed in glass and has a length L and width W, respectively, of 64.3 centimeters and 48.2 centimeters, correct to 0.1 centimeters as shown in the diagram. A, find the bounds on the measurements of L and W. Okay, so let's start with A. And we will take a look first of all at the length. So the length is 64.3 centimeters. And the precision of the instrument or the ruler with which they measured was 0.1 centimeters. So p halves would be then 0.05 centimeters. And that's what we need to use to find the bounds for L and also for W. So for L, notice that if it's 64.3, we subtract from this 0.05, we're going to get 64.25 centimeters, less than or equal to L, less than 64.35 centimeters. And then we have that the width, W, is equal to 48.2 centimeters. And then we would do the same thing. We would subtract the 0.05. So that would give us 48.15 centimeters as the lower bound. And this is for W. And that has to be less than 48.2 plus the 0.05. And that's going to be 48.25 centimeters. Okay, so with this information, we're going to find the maximum area and the minimum area, which is what we will need to find the bound on the area A. So that's part B. So the maximum area would be where the measurements are maximum, right? So that means a length of 64.35 times a width of 48.25, and that is going to give us about 3,000 104 centimeters squared. So that's going to be the upper bound, right? The maximum. And the minimum area would then be the result of multiplying the minimum measurements. So that would be 64.25 times 48.15, and this equals 3,093 centimeters squared. So that means that the area would be bound by these two numbers. In other words, 3,093 centimeters squared would be the lower bound of the minimum for the area, and the maximum would be 3,104 centimeters squared. So those would be the bounds. So how can we compare this? Well, for part C, because part C says compare the level of precision of A to that of L and W. So for L and W, the precision was 0.1 centimeters. But for the area, the precision is going to be the difference between these two numbers. So we would have to subtract 3,090 or 3,104 minus 3,093, and that gives us 11 centimeters squared as the precision for the area. Okay, and the next topic is percentage error of measurements. And it says, if we want to quantitatively judge how well a measurement approximates an exact value, we use the concept of percentage error of the measurement, written percentage error. The percentage error in a measurement states the difference between the measured and exact values as a percentage of the exact value. In symbols, percentage error equals exact value minus approximate value divided by the exact value. They're forgetting something here in this formula, and it's the fact that we have to multiply the result of this division by 100, right, if we want to get the percentage error. And it says, note that the percentage error can be positive or negative depending on the relative sizes of the exact value and the measured value or approximate value. Okay, so let's rewrite the formula. It's exact value minus approximate value divided by the exact value, this times 100. This would give us the percentage error. Very well, and now we are on example 1.8. And it says a meter stick correct to 1 centimeter is used to measure the height of a person as 176 centimeters and is also used to measure the length of a piece of paper to be 12 centimeters. Find the magnitude of the maximum percentage error for each measurement and interpret its value. Okay, so let's start first with the height, right? The height was measured to be 176 centimeters. And the precision of the instrument, of the meter stick, is 1 centimeter. So P halves would equal 0.5 centimeters, half a centimeter. That means that H would be bound the following way. It's going to be greater or equal to 175.5 centimeters, and it's going to be less than 176.5 centimeters. So how do we calculate the percentage error of the measurement, right? If we found it to be 176. Okay, so remember that it's going to be using the formula that we just saw in the previous slide, and we would consider these to be the exact values. This would be one exact value here to the left, and this over here would be considered the other exact value. and then we would compare 176 with those two values. So remember that it's the formula is exact value minus approximate value over the exact value times 100. Okay, so in that case, let's first compare it with the left bound. So we would say, all right, 175.5 minus 176 divided by 175.5 times 100. And this is going to give us a negative 0.285%. So that is the percentage error when we compare it with the left bound. If we compare it to the right-hand side, let's see what happens there. We would get 176.5 minus 176 divided by 176.5 times 100, and this would give us a positive number of 0.283%. Okay, then if we compare these two percentages, we can see that the greatest percentage is, or the maximum percentage error is this one, right? So a maximum error of 0.285%. Okay, so now let's do the same, but for 12 centimeters. So we would say the length is equal to 12 centimeters. The precision of the instrument is 1 centimeter. So p halves would be 0.5 centimeters. Next, we would find the bound for this. So it would be 11.5 on the left, less than or equal to L, which would be less than or equal, or no, just less than 12.5 centimeters. So let's calculate the percentage error. And it's going to be 11.5 minus 12 divided by 11.5 times 100. And this will give us negative 4.3%. Okay, and then the same thing with the right-hand side. So we would say 12.5 minus 12 divided by 12.5 times 100. And this would give us exactly 4.0%. So in this case, that means that here we would have 4.3% as the magnitude of the maximum percentage error for the length. So this one was minus 4.3%. And remember that before for the height, we found the error, the maximum error to be minus 0.285%. Now, because they talk about the magnitude, really the negative sign doesn't matter. So when we compare these, we notice that this is a much higher percentage of error. Now, why is that? Or I can state, I should say actually, that it is because when we make a smaller measurement, precision influences the error, right? Because if you measure the height of a person and it's approximately 176 centimeters, and your error or your precision is 1 centimeter, that is less affected than if your error is 1 centimeter in 12 centimeters. So that's the reason.